Hello everyone. The advantages of a completely randomized design or CRD are only applied when the experimental units are reasonably uniform. If the experimental units are not uniform, a CRD will have a large estimate of experimental error and the biased treatment effect. This could lead to a false conclusions. These are the lecture aims. We can overcome the limitation of CRD by using blocking designs. In addition to replications and randomizations, these designs implemented the third principle of experimental designs, the reduction of experimental error or blocking. There are several advantages of blocking designs. In blocking designs, residual variance is partitioned into the among block variance and the variance due to random residual. The blocking will take into account the systematic variability among experimental units. The experimental units can be blocked by time or person. However, this design also has some limitations. When there are missing values, the analysis is not straightforward, as block effects could become confounded with treatment effects. A CRD maximizes the residual degrees of freedom. Blocking designs reduce the residual degrees of freedom by partitioning these into block degrees of freedom and error degrees of freedom. Remember that the error mean squares is the estimate of experimental error, and it is calculated as the error sum of squares divided by the error degrees of freedom. So, smaller degrees of freedom could cause a larger estimate of experimental error. The experimental units in a block must be more uniform than across blocks. In a balanced complete block design, a block must contain a complete set of treatments. An experiment with many treatments will require larger blocks, and it is often difficult to find a large uniform block. In CRD, we partition the total sum of square into the sum of square due to treatment and the sum of square due to residuals. In blocking designs, we further partition the sum of square of residuals into the sum of square due to the blocking factor and the sum of square due to random residuals. Depending on the designs, we can have more than one blocking factor. The linear model, a randomized complete block design or RCBD is the most straightforward blocking design. RCBD is used to take account of systematic variation that occurs across experimental units. In this design, experimental units are divided into blocks. The experimental unit within blocks are more uniform than the experimental unit across blocks. So the within block variance is smaller than the among blocks variance. When the heterogeneity occurs in a gradient, the blocks must be laid out in the right angle or perpendicular to the direction of this heterogeneity. When the heterogeneity occurs in patches of area, the block must be laid out to match these areas. Treatments are randomized within each block. Each treatment occurs once within each block, so each block contains a complete set of treatment. The number of replications is the same as the number of blocks. For RCBD, the total variability is partitioned into among block variance, among treatment variance, and variance due to random residuals. The ANOVA table the linear model, for an RCBD experiment, in addition to the hypothesis testing for the treatments, we can also do hypothesis testing for the blocks. The hypotheses for the treatments are the same as in CRD. The hypothesis for the blocks, Let's see an example. Because of this fertility gradient, we cannot use a CRD. In this case, we have to use an RCBD with the number of blocks equal to 6. The blocks are perpendicular to the fertility gradient. Each block contains a complete set of treatments. Before we do the analysis, we should write down the skeleton ANOVA. The ANOVA for this experiment, at a 5% significant level, the p-value for block is less than 0.05, so there is a significant block effect at the 5% significance level. Let's compare this with the result from CRD. Because the block is significant at the 5% significance level, the among block variant has accounted for a considerable proportion of the residual variance. Therefore, the RCBD has a smaller estimate of an experimental error, which means for this experiment, the RCBD is more efficient than the CRD. RCBD only takes account of one additional source of variability. The blocking is one-dimensional. If there are two additional sources of variability, we can control these variabilities by blocking in both directions or two-dimensional blocking. We refer to these two dimensions as rows and columns. In this case, we partition the residual sum of square into the sum of square due to rows and the sum of square due to columns and the sum of square due to random residuals. A Latin square design is one of two-dimensional blocking designs. Do you know this game? Do you know the rule of this game? This is a Sudoku game. The rule of this game is each number must occur once in each row and once in each column. This rule is similar to the rule of a Latin square design. In a Latin square design, the number of rows is the same as the number of columns. And the same as the number of treatments. Each treatment occurs once in each row and once in each column. So, the number of experimental units is the square of the number of treatments. And the number of replication is equal to the number of treatments. A Sudoku is a Latin square design for 9 treatments, or a 9 by 9 Latin square. A Latin square design is useful for controlling 2 sources of variation. It is commonly used for animal experiments and can be more efficient than a CRD, especially when there is a limited number of experimental units. For example, we can use a Latin square design to assign the treatments. In this case, we assign weeks as rows, and cows as columns. Each diet occurs once in each week and assign one for each cow. However, the Latin square designs have several limitations. If the number of treatments is less than 5, the degrees of freedom for residual is less than 12. For k treatments, we need to have k-square experimental units. So, for 10 treatments, we need to have 100 experimental units. When the number of treatments is large, a Latin square design becomes impractical. No interaction implies that the treatment effect is the same for each row and each column. For the Latin square design, the total variability is partitioned into among rows, variance, among column variance, among treatment variants and variance due to random residuals. The ANOVA table the linear model, for a Latin square design, in addition to treatments, we can also do hypothesis testing for rows and columns. The hypotheses for treatments are the same as the one for RCBD. Hypothesis for rows, hypothesis for columns, let's see an example. We can use a 6 by 6 Latin square design. Each treatment occurs once in each row and once in each column. the skeleton ANOVA, the ANOVA for this experiment. At 5% significance level, there are significant row and columns effects. Let's compare this with the result from the RCBD. Because both rows and columns are significant at the 5% significance level, the Latin square has a smaller estimate of experimental error, which means it is more efficient than RCBD. Row column designs are modern designs that optimize treatment allocations in both directions. These designs can be applied to any number of treatments and replications, with the number of treatments is equal to the number of rows by the number of columns. While there is no restriction that each treatment must occur once in each row and once in each column, this design optimizes the occurrences of treatments across rows and columns by minimizing the number of times pairs of treatments fall together in each row and each columns. There are many variations of the row column designs. A resolvable row column design is the most straightforward row column designs. This design has a similar arrangement as RCBD and can be analyzed as an RCBD experiment. These designs optimize the occurrences of treatments across rows and columns within each block. For the resolvable row column design, the total variability is partitioned into among block variance, among rows within blocks variance, among columns within block variance, among treatment variance, and variance due to random residuals. The skeleton ANOVA, The linear model. In the resolvable row-column design, treatments are optimized across rows and columns within each block or replication. We can also optimize the treatments across blocks. This is known as Latinization. If the blocks are laid up along row, we can do row Latinization. The treatments are optimized across the long rows. The skeleton ANOVA. If the blocks are laid up along columns, we can do column Latinization. The treatments are optimized across the long columns. The skeleton ANOVA. If the blocks are laid up along rows and columns, we can do row and column Latinization. The treatments are optimized across the long rows and the long columns. The skeleton ANOVA. Block when we can and randomize when we cannot. For fill and glasshouse trials, a row column design is highly recommended. The row column designs are flexible and provide insurance against two-dimensional variability. We can use a free online software such as DeltaGen to generate a row column design. Now, can you do this?